I'm Joseph Thompson. I'm a senior in mechanical engineering, and I'm the group lead for Group 4 for the ranking cycle. So our objectives for this experiment are to understand just the basics of what's going on in the ranking cycle, how we get power out of it. We need to be able to measure the data from the lab and use that to calculate important parameters about the cycle, such as the overall thermal efficiency, that make charts for fuel flow versus time, generator amperage output, and voltage output versus time, and other important parameters that you need to know for a power generation cycle. So for some background, in 1859, William Rankins, Scottish engineer William Rankine, made this theoretical process for having a closed loop vapor power cycle so you can extract energy from heat. And today it's used for about 90% of all of our electrical energy production. And then here's a basic diagram. So we, water enters a boiler in a liquid state, and then it's heated up by a fuel source. One of the reasons why we don't just use the direct fuel source into the turbine is just because you can burn kind of whatever you want. It can be super nasty, like a coal, and which would clog up a turbine. So we use that to heat up the water, and then it enters as enters the boiler as a liquid, exits as a superheated steam, goes through the turbine, and inside the turbine that's where the work is extracted from the steam. And then it exits still as a vapor, and then in the condenser, heat's rejected from the steam, and then it condenses into a liquid, and it's pumped back into the boiler to complete the cycle. So your work out's in the turbine, work in is in the pump, and then heat goes out in the condenser and in the boiler. All right, and this is what the TS and the PV and the TS diagrams look like. So this kind of just shows basically just from one is where the it's pumped into the boiler, and then temperature increases, becomes a vapor, and then comes down. These are like the idealized versions of this, but in reality, if you have any kind of condensation in the turbine, it'll cause wear on the parts, and you can't have, you need to make sure that it's the liquid entering a pump is all liquid, because the vapor in a pump will cause issues and maintenance problems. And then, so the ideal versus the real cycle, you can kind of see how the red dashed line is the ideal, and then in reality there's heat loss in pipes, frictional losses, and again, you can't be pumping, having steam condense in a turbine or a vapor entering your pump, so you have to be work within a margin of error. So you can kind of see the difference between those two lines is where your efficiency losses are. All right, so our equations for our work, when it's pumped to the boiler steam generator, it's just the difference in enthalpy across that, and then the heat added in the boiler is the difference in enthalpy when it's entering and exiting. Work extracting your turbine, it's just all differences in enthalpy basically, and then the work is the difference in the amount of work that you got out from the turbine compared to the work that you had to put in the pump, divided by the heat that was added to the water in the boiler. All right, so we can improve our efficiencies by using a regenerative or a reheat ranking cycle, and you can do this in multiple stages, but this is kind of the most simple version. So in reheat, which is on the bottom right here, you have a high and a low pressure turbine. So when steam exits the high pressure turbine, it goes back to the boiler to get reheated, and then it goes into the low pressure turbine, and then that kind of completes your cycle, and you can get a little bit more efficiency, sometimes like 3 to 5%, which whenever the thermal efficiency of a normal ranking cycle is about 50, that's pretty good. And then the regenerative just uses a open feed water heater to just regenerate, and it kind of creates a separate cycle within it. So, yeah. And then this is our experimental apparatus. There's, this was kind of covered in the other presentation, but we have the condenser tower, our fuel source, and our boiler. There's no pump in this because we measure the fluid collected out of the condenser and the fluid that's left in the boiler to figure out how much water was what went through the process. So for our procedure, make sure everything's shut off, clean, and then we drain the condenser towers and make sure that everything we have a baseline for our fluid level, and then you fill the boiler, plug everything in, make sure all the DACs are on, and then you connect the fuel source. You have to make sure you're not leaking, and then we turn everything on, and then once it's heated enough, you set it to output about 0.2 amps and 6 volts, and have a boiler pressure of about 110 psi, and then let it run for 10 to 15 minutes. And then we measure the condensate collected, measure what's left in the boiler, and then save all the data, and then that's pretty much the experiment. Then it's all data interpolation. So.